applications. So I'm going to do something a little bit different. It's going to be a little mix of a bit of technical and a bit of the space industry itself and how machine learning plays into all that. So really what this is about is how do we transform raw satellite imagery that comes down at like a huge monster petabyte scale and convert that into something we can use. And in our case at EarthDaily Analytics, we're doing this for environmental reasons, for agriculture, for forestry, for water management. And so I'm going to dive into a few of those applications. But first off, just a bit about us. We are a software and information services space company. What that means is we design satellites, we put them into orbit, but our fundamental reason of being is around the software and how do we convert the data you get from satellites into meaningful, actionable information. So we do a lot of satellite processing, we do ML extraction of data, but it's really about getting to answers, not just about creating pretty pictures. So I think when most people think of satellite imagery, you probably think of Google Earth, and there's a little image of Vancouver there. That's where I'm from here. But in the world of space, it's more than a pretty picture and more than red, green, and blue. It's really about seeing the world with different frequencies of light. And with that, you can start extracting really meaningful insights. And one example there is at the bottom. That's one of our platforms we use for agriculture. And what we do is do crop health prediction and recommend to farmers what sort of applications to put on their field so that they can be more productive with their crops. But before I jump in, I just wanted to touch on one thing, because I'm always blown away by how far we've come as a civilization. Space, even the concept of it, never really existed that long ago. I think the first recorded novel was back in 1865 by Jules Verne, From the Earth to the Moon, where he imagined us building a spaceship and then going off to the moon. And the crazy thing is that we did this in about 100 years. And this is going from nothing. At this time, back in the 1800s, we didn't have planes. That only came by the Wright brothers back in probably the early 1900s. But by 69, Apollo 11 landed on the moon, and we were then a spacefaring species. And so we were set foot, and we haven't looked back since. But where we're at today is actually even more mind-blowing. There's been this crazy exponential increase in the number of satellites being launched. And I think most of you have probably heard of space junk. And now when astronomers look up, they see the Starlink satellites. And so this is becoming a problem. We have so many satellites that have been launched in the last 10 years. So we have this exponential boom of satellites. Fortunately, now they have these regulations that say you have to take your satellites out of orbit when you're done. So as part of our constellation that we'll be launching, we'll deorbit it, basically bring it down, and then it burns up in the atmosphere and it's gone. But the crazy thing here is you see this big ski jump in the last 10 years. And this is brought about by a couple things. It's called the new space revolution. But what it really means is really crazy innovations by companies like SpaceX have figured out how to launch satellites cheaper. And in addition to that, we now have miniaturized computers. So cell phones have more power than the data centers back in NASA in the 60s. And so we can shrink these electronics, put them on satellites. In fact, today we have satellites that are the size of my mug that are imaging and doing some pretty remarkable things. Of course, you're battling laws of physics, and they're not going to be as good as your bigger satellites, but still, we can do that. And so this is one of the big transformations that have happened. Now, alongside with that, there's been a big change in how we view and how we use machine learning. This started back in 1950 with the term machine learning, but it's been changing rapidly in the last 10 years. And now it's pretty much part of almost every industry where we're using in some mechanism by either business metrics or delivering insights from different types of data for monitoring, all sorts of different things. So the last 10 years has given a boom to the space industry. It's given a boom to ML. And then what all ties us together is this enormous change in how we can handle compute and storage. We've had satellites for a while, but for us to really exploit or use that data in any meaningful way has been really tough. And in the last 10 years, AWS, Google, Microsoft, IBM, there's other cloud providers who are now providing services that makes it so easy for us to have a supercomputing facility. And that's what most companies do nowadays. We all leverage the cloud. We use our Lambda functions, serverless compute, or EC2 instances in AWS speak. But this is really enabling what we think's coming up. And I think someone, I don't recall who coined this term, but the fourth industrial revolution. And it's really an AI-driven economy where we use the information we can extract from machine learning and AI to derive really meaningful insights. And so in the space world, we have this perfect convergence right now. We're at the cusp of a new revolution in the space world. I'm convinced of it. And we don't have a name for it yet, but we're just walking out of the new space revolution and into, I don't know, it's like a new ground revolution where we're taking the cloud, we're taking machine learning, we're taking the data from these satellites and extracting a whole bunch of insights about how the world operates. And this has been a vision for Earth observation for a long time. Landsat-1 was the first science mission really designed to image the Earth, see the signals on the ground, understand forestry and vegetation. But at the highest level, we use the term Earth observation to mean look at the world from space. And what we're doing is just measuring reflective signals that are bounced off the Earth from the sun, and then we capture them. It could be either thermal signals, it could be red, green, and blue. It could be things called shortwave infrared. But really, at the end of the day, the dream of the space industry, and myself included, is really to use satellites for the greater good and help some of the most pressing challenges we face today. And that's what we've all been striving to do. But because of, in the past, the lack of the compute clusters, because of an inability to process all the data or meaningful extract trillions of pixels, we've been kind of stuck. And now we're just on that verge of unlocking things. So this is what we're doing at EarthDaily Analytics. We believe that many of the greatest challenges that we face today can be solved if you can produce a scientific mission. And when I say scientific, I mean measuring reflective signals on the ground precisely, not with huge error bars, but like really good signals so you can infer the underlying physical processes. But if you could do that, and if you could apply AI, you could do daily enterprise-grade change detection. Enterprise-grade just means trusted. Change detection where if you see a change, it won't be riddled by false positives, but an actual reliable change. And then you can get into alerting and predictive analytics. Some really simple examples are in deforestation, about half of it is due to illegal deforestation, illegal cutting. And so if you can see the whole world every day, you can see where that illegal deforestation is happening. You can contact the authorities, you could send them out there, they could deal with that problem. But it goes even beyond that. Sometimes by the time you're seeing it, it might be a little bit too late because when you're clear cutting forestry, you kind of do the interior and the crowns kind of cover the tops, you don't see it right away. But you can actually have telltale signs. And this is where if you have sophisticated AI or machine learning, you could actually predict where deforestation might happen. For instance, if a road's being built where it shouldn't be, you could detect that road without looking through trillions of pixels with your eyeballs. You could easily do that with computer vision or ML, and then again, do an alert and react to it. And so we see broad area coverage of the whole globe being key to things like agriculture, improving global food security, helping with climate change and making sure we're doing carbon sequestration properly with different practices, whether it's maintaining forests or doing regenerative agriculture, things like disaster response and habitat protection. So there's a whole bunch of different applications we can use satellite imagery for if we can unlock it with fast, reliable compute and good, accurate ML algorithms. And just for those of you who aren't familiar with the space world, the concept is quite simple. And this is how most satellites work. Typically, a satellite gets tasked. It's essentially the program of what to acquire. So it might be imaging Vancouver, it might be Montreal, Toronto. But essentially, it'll get a command to image Toronto. It'll fly over Toronto, turn the camera on over Toronto, grab that image, which is simply the sun reflection off the surface, and we capture that image. And then you fly over a big antenna. We call it a ground station, and that downlinks this raw bit stream. It's kind of like how you imagine satellite communications or satellite TV. It just basically downlinks the information. But once you get it there, that's where the magic happens. These aren't like cell phones where you can just take a picture and out pop a really fancy, nice image. There's a lot of processing that has to happen on satellite imagery. You have to model the shape of the Earth, the atmospheric effects, how the satellite's kind of moving in orbit, if it vibrates, the distortion of the optics. I mean, it's a very complex problem. And then doing that at scale becomes the next challenge. So what we're doing at EarthDaily is we're in the process of building our satellites right now. We are launching next year, so it's right around the corner. We're super excited to be getting these satellites in orbit. We've been designing them for many, many years, and we're finally at the point where we're pulling the trigger. Here's a little video of what conceptually it looks like. So the way it works is we turn our cameras on whenever we're over land. So it's basically like a Hoover or like a vacuum cleaner, just kind of siphoning up the Earth, monitoring the whole planet at about 5 meters resolution. So we're not reading license plates here. This isn't a spy satellite. This is global coverage. We capture many, many pixels, trillions every day. And we're also capturing maritime areas. So you can see what's happening on the coast. You can see that there's kelp farms now that you can actually watch and see how they evolve. And these aren't tiny little satellites. They are 200 kilograms in mass. So they're like the size of a big flying oven. They'll live for about 10 years, and then we'll deorbit them. We'll bring them down. They'll burn up. But what's really unique, and I think we're the first commercial space company doing this, we're basically looking at the full spectrum. We're looking at visible and near infrared. We have 11 different colors or spectral bands. We're also looking at something called shortwave infrared, and then thermal. So we have all these different signatures. And I like to think of it as if any of you have seen Life in Color with David Attenborough, and he shows pictures of butterflies, and you can see ultraviolet and all these different wavelengths. That's what we're doing of the Earth. We're looking at it at all these different frequencies so we can see the underlying physical processes. And then we can see how we can build models of how water's evaporating and that will help with water management where we'll experience droughts. So there's all these really sophisticated things we can do when we're using all these different bands. But the core challenge for the software engineering team that we have is we have 100 terabytes of data per day if you uncompressed, and you can compress it gets smaller. So how do you build these data pipelines with this much data just flowing through the system every day? And by the way, maybe you want to do some reprocessing of yesterday's data because someone wants it tweaked and done a little bit differently. So it could exceed that. So we have these huge monster volumes of data. And traditionally, this is done through manual processing. If you go back 5 to 10 years, there's humans in the loop. It's almost like Photoshop, where you find a feature in your satellite image, you look at Google Earth, and then you stretch the image out. You kind of like, we call it rubber sheeting, you just stretch it out. But we're not doing that here. We're using rigorous physical models, and we're doing this automatically with computer vision and machine learning. And so we have this technology in Vancouver that we built over the last 9 years. It's called the Earth Pipeline. It allows us to transform raw data, and this is kind of a representation. True raw data, you can't really visualize it, but it has artifacts. It doesn't really look like a good image, but after you process it, then you get something that looks like the image on the right. And now you have a latitude, you have a longitude assigned to it. And every one of those pixels is accurate, both in terms of the color, which we call radiometry in scientific speak, and in terms of the location. And so this is where we tie in machine learning, computer vision, and physics is also very important to us. Essentially what we do is we build a digital twin of our satellite. So we model all the physics we can, how it's jittering, the optics, the orbit. But you need more than that because you don't know precisely where your satellite's located. So we have to augment it with other external data. And this is where we've developed some really cool technology for machine learning to help us with some of the challenges. And so one of the first things you do in satellite image processing is you look at a reference image and see how well your image matches up, because typically you're going to have errors of kilometers, but you want to know the pixel down to a sub-meter accuracy. So what you do is if you look at this image here in the middle, you have near infrared, and it looks very different to your reference image that's shown in that green box. But what you want to do is align that. Now, traditionally, you use your eyeballs and you can match those up, and that's part of the manual work that operators do. But now, of course, we have computer vision and we have machine learning. And so we've been applying some of the normal computer vision algorithms that have been around for the last decade and more, and they work fairly well, but they break down when you use that near infrared band versus that reference band. Green and red, they look pretty much the same, so it's a simple computer vision problem. We can tackle that. But near versus reference is hard. And so we developed this deep learning based correlator. We called it ML Core because they're not very creative, so we need a better name for it. But essentially, it was the challenge here was developing the right CNN, but also training. It was a huge amount of training we found we needed. We needed 18 million of these chips to actually get some good results. Without that, it just wasn't robust with the nature of satellite imagery. But at the end of the day, what we found is it was an experiment and we weren't sure if it would work. But at the end of the day, this correlator actually worked far better than some of these physics-based ones that have been proven to work well in industry. And they generally work pretty good. But yeah, it's like most people, once you start diving into machine learning and deep learning, you find it able to solve these interesting problems that don't really line up with the quality you would get with physics-based approaches. And so what we're seeing is this ML correlator really locks onto the geometric features as opposed to the color features. And that really gave it a little more sophistication and ability to get more accurate values. And that's what you're seeing in the top there. It just gets a slightly better number. But that's meaningful when you're trying to do this all automatically in 100 terabytes of data per day. The other place where we use deep learning is for cloud detection. And so I did skim over the fact that we're imaging the whole world every day, but there are clouds, right? Probably on 50% of the planet. So you can't see through clouds with optical imagery. There are certain space modalities where you can. It's called synthetic aperture radar, but that's a different talk, which we also do some work there, but our main focus is optical. But clouds are super easy to see with your eyes. Like you look at a cloud, you know it instinctively. But this has been plaguing the Earth observation industry for the last 20 years. It is notoriously difficult to detect clouds with algorithms because clouds have so much variability. Sometimes they're wispy, sometimes it's just a bit of haze, sometimes they're thicker, sometimes they have lots of shadows within them. And the definition of a cloud is tricky. So what they've done is created specialized filters on satellites that can detect clouds. But the challenge here is that not all satellites can afford these really expensive filters. And so we went into the approach a bit differently, and others are doing this too in the space industry. But we started tackling this with machine learning. So we built a CNN for this particular use case, and it actually worked really well. We found in some cases it could significantly outperform the physics-based approaches, which weren't very good at detecting haze. And you can see some examples of that on the left. You basically have a nice mask, relates well to the truth. And sometimes we found that our mask did better than our ground truth. And that was just one of those interesting things that sometimes pops out of machine learning, that you discover that your training data isn't that good. Yeah, so it worked out really well. And that's our way forward with how we process satellite imagery to leverage these neural nets to help. And that's how we evolve our technology. The other place where we use computer vision, and computer vision is more the broader term, but we also use deep learning as well. We do reconstruction of imagery to make it sharper. And so there's two forms of this. There's one that is purely physics-based. And you can see an example of that on the top. And you can see hopefully it turns out a little bit in the video. It's a little bit sharper. But it's not like in the movies where you can zoom in on a license plate and then read it from afar. But this is very accurate. There's no false information. There's also another approach we're doing it. We can do it called super resolution, which employs deep learning. And we have a partner at the University College of London. So shout out to them for doing this. But they use a neural net, and you can get a much higher resolution, but you can occasionally get fake news. So if you want to really know what's in the imagery, and an error is very bad for your application, you wouldn't want to use this. But if you want to know statistically, what do you think the imagery looks like? It does a fantastic job. And just the last application I'm going to talk about, one of our big areas of development is in agriculture. So one of our customers wanted to know, could you tell us where all the pivots are across the whole planet and how many there are? And this is a perfect ML example. There's no human operations team that could count all the irrigation pivots across the entire planet, because there's so many millions of these pivots. And essentially what an irrigation pivot is a mechanism that irrigates. And you can see a little example of that on the top right. But essentially what we did is we developed a machine learning algorithm to basically go through, find these little circles. It was quite difficult because in some years they don't show up because it rains. And if it's raining, you don't actually need your irrigation pivot. And so what we found was, in some cases, it was hard to detect. So we had to do some interesting time series modeling. So we'd have to look year over year and see where they're popping in and when they're popping out, and then factor in the weather forecast and feed that into our model. So it got really quite complex at the end of the day. But overall, it worked really well. We had some good truth over Brazil. And that's a place where it's really hard to monitor because there's lots of clouds due to the weather patterns. But we were able to get 90% recall versus some public sources. So again, this is a case of, as we adopt machine learning into our processes, we're finding it just works phenomenally. And we're going to continue to grow our Earth observation applications with machine learning. And that's a really quick summary of what we do at EarthDaily Analytics, how we employ ML, and our big mission coming up. And I guess like the others, I'll do a shameless plug. We are looking for people to help with our software, big data pipelines, and machine learning, and you name it. We're doing lots of hiring right now in Vancouver. So yeah, I'd love to hear from you if you're interested.
Way to go, Chris. Thank you so much, sir. What's the stack?
Oh, yes,
what are you looking
many
for?
different things. So we do use a lot of Python. We use a lot of, so we do a lot of numerical analysis. So we use scikit for some of the ML. We use PyTorch. We use NumPy. I think I said that's SciPy. AWS is our cloud solution. So we do a lot of Lambda functions. Our technology actually looked a lot like what I saw Andrew present. We use Jenkins, and we use GitLab, so instead of GitHub. But yeah, it's a lot of Python, a lot of back-end work. We do some front-end work, but most of our stuff is the algorithmic on the backside.
Interesting question here by Alex. Alex has asked, has EarthDaily thought about how their tech could be used to counter fake news? He's kind of gone on to say the current events happening in Ukraine and the misreporting of these events in Russia comes to mind.
Yes, there's
thoughts there for you.
Satellite imagery is very relevant right now, and I'm really proud that it can be helping with some of the issues in the war in Ukraine. It's a horrible thing, as we all, I'm sure we're all, our hearts go out there. But yes, this is one of the things where satellite imagery can definitely do the fact finding. And one of the mandates behind our mission is to be auditing environmental type applications, but it could also be used for seeing where troops really are. Again, we're not a high resolution mission, so we're not a defense company. A lot of companies specialize in going to like license plates. That's not our thing. But if we want to say where there's large troops allocated, we can definitively show that across the world. And if troops are moving in a certain location, if tanks are kind of coming from one country to the next, we can spot that and say, hey, what's going on here? We can do alerts on that. Even strange movements, troop movements, we'll see that. Again, we're not going to see individual people, but we will see large objects, the tanks and that. So that's a great idea, Alex. And I think that's something our constellation could definitely help with. We're looking forward to getting it up online in 2023 and using it for things like that.
Bit of a product deviation maybe, but hey, some food for thought. Build it and they will come. Awesome, Alex. Thanks for that, bud. So we've got a question here from Ayaz. Ayaz has asked, at the scale of sheer raw data and the number of images that are required to train ML Core, how do you detect and deal with model data drift?
Yes, that's going to be a key challenge. So I'll back up with a bit of history of what the current challenges are. Right now, the big issue that we face in Earth observation is the 80-20 rule, which probably applies to other ML industries, but 80% of the time is just normalizing the data and 20% is extracting the insights. And this has been extremely true for EO because data is really hard to normalize. Now, in our case, we have, it's probably another conversation, but we have some techniques to ensure our data is well normalized based on how we're calibrating our satellites prior to launch. This is very different than other people are doing it. So our sensors will be highly normalized between every individual sensor. And we actually use this daisy chain approach where every satellite intersects every other satellite. So what that means is every image will look virtually identical as we acquire it. And that's very different than other satellites out there. And so then if things start changing and requiring data every day, that drift will be observed in some kind of metric. I would imagine whether it's increasing number of false positives or the alerts are getting, the percentage of reliability is going down of detection. And so if things are changing with the sensor or the model, I think because of how we've normalized our data, it should be evident. But that's a good question and something we have to think about deeply as we put our constellation in orbit. Nice
one. Thanks for the question there, Ayaz. We've got another one here from Alex. Alex has asked, have you considered using or training image classifiers on your image data set like CLIP, CLIP?
So I'm not familiar with the CLIP. So I'd love to talk more about that. It sounds interesting, but I'm afraid I'm unfortunately not familiar with that. So I'd love to say yes, but we could. But yeah, maybe we should connect after.